So in the last video, we defined a cluster point. We gave some examples of what was or wasn't a cluster point. And it seems to be that the key idea of what makes a point a cluster point of S is that stuff in S gets arbitrarily close to C. And as we sort of alluded to, we already have had a notion of arbitrary closeness in this class, and that is that of convergence, right? Of sequences converging to C. And if we even look at the picture that we have over here, we have C, there's stuff in S getting closer and closer to C. We should be able to see, look at that and visually imagine a sequence of these red dots getting closer and closer to C as well. And so we shouldn't have these two separate notions that deal with arbitrary closeness and not be able to see some sort of connection between them. And so this video, we're going to prove this proposition that given some subset of the real numbers, S and R, and if C is a cluster point for S, that occurs if and only if there exists a sequence going towards C of stuff in S, none of whom are actually C. So excluding the constant sequence C. All right. And so let's go ahead and prove this. Let me switch colors here. And let's go with the forward direction. So we're going to have our cluster point and we're going to have our sequence going towards it. Now, the intuition behind this is I want to be able to, if I pick some sequence, some distance, some epsilon, there's stuff in there, right? The cluster point definition guarantees that I have things other than C in that radius. So I'm going to pick one of them to be x1. Then I'm going to go in closer. There's more stuff in here. I'm going to pick one of these to be x2. Then we go in closer. I'm going to pick one of these to be x3. And so it's not monotonically getting closer and closer to C necessarily. But the point is, if I keep doing this, it's going to force how far away I could be. Right? All of these points are now getting closer and closer and closer to C, and in doing so, I'm building a sequence of stuff converging to C. So let's incorporate all of that into this proof here. For every natural number, we know that C minus n, C plus n, delete C, intersect S, intersect S, delete C. That whole thing is not empty, right? By the definition of being a cluster point. And so, 1 over n, because we want these things to get closer. So I start at 1, then go 1/2, 1/3, 1/4. Each step I go in, I'm taking smaller and smaller intervals, but none of those things all of those things always contain some S elements. And so we're just going to let x of n be in this set, be in C minus 1 over n, C plus 1 over n, intersect S, delete C. Then we want to show that this x of n, in fact, converges to C. So we let epsilon be greater than 0, and then by the Archimedean principle, there is a big capital N in n such that 1 over capital N is less than epsilon, right? This is one of the two-part equivalent statements of the Archimedean principle. So for all little n greater than equal to big N, we know this. We know that the distance from xn to C, that's less than or equal to 1 over n, which is, strictly less than 1 over n, and less than or equal to 1 over big N, which is itself strictly less than epsilon. So, for any epsilon, these x sub n's get to be within epsilon of that C. So, that proves that this sequence converges to C. Reverse direction. So in the reverse direction, what we have instead is that we have a C and there's a sequence of S stuff converging to C. Now note S could contain a lot more things than just this sequence, but we don't care necessarily about all of those things. Remember, we just want to take intersections around C and show that it's not empty. So as long as we can find anything, that's good enough. I don't need to know everything that's in there. So here's my xn's, they're all coming in. I want to show that for all my choices of epsilon, there's always stuff in there. So let epsilon be greater than 0, and then we note that there exists a capital, well, you know what, we'll just say this. There's going to be some n in N such that the distance between N and C is less than epsilon, right? If these xn's are actually converging to C. And then we also know that xn isn't C itself. That's part of our hypothesis here, right? So if I take C minus epsilon, C plus epsilon, intersect it with S and delete C from all of that, that contains x sub n. So it's not empty, so C is a cluster point. All right, thank you. I hope that was informative and that made sense. See you in the next video.